Alright everyone, so today we'll be doing chapter 24b. Let's see some of the problems. So today we'll be doing conversions and specifically which values these Maclaurin series will converge. So the first problem we have is cosine x equals to 1 minus x squared over 2 factorial. Let's see if this is working. Yep, I think everything is good. Okay, so let's get into this one. I think we have cosine of x equals to 1 minus x squared over 2 factorial plus x power fourth over 4 factorial, and we have more, right? So what we're going to do first to find the conversions, values conversions, is we have to find the summation. So let's start with that. So let's do n equals 0, infinity, and then let's see this pattern, right? So we have this alternating sign. So an easy way we can deal with that is by doing negative 1 to the power of n. And then here in the numerator we have a increasing like exponent to the value with the value of 2. So we can just do 2 times n here. And denominator we have a factorial, and I think this is also increasing by 2, so we can just do 2 in factorial, right? And that should give us a summation. And then we can use the radial test. So what that would look like is we have limit of n approaching infinity. And then, why does it do that? Is it this one maybe? Yeah, let's try to turn that off and see what happens. And then we can do n plus 1 for the top term, and then n just equals to whatever value n is in the bottom, right? So we can actually take out this term, doesn't really matter when we do radial test because it's kind of absolute valued. So we're going to do x2 n plus 1 because the 2 multiplies to the 1 as well, I think. And then we have here in the denominator we have 2, also same thing, n plus 1. So make sure we get everything multiplied in here. And denominator, we write the same thing as a summation formula, just the exact same thing. So 2n factorial, right? So now let's move down here. Let's see if it let me draw the infinity sign this time. Yep, let me draw it. Okay, nice, perfect. So we can convert these two fractions to 1 by doing x2n times, I think this is actually x squared if I did this correctly. And then down here it should be, oh shoot, sorry, I'm missing one more term because we still gotta bring this over here. And yeah, denominator we have the 2n, I think this is plus 2, yeah, factorial times x 2n, right? And now we can see some clear things we can get rid of here. So let's start with the x2n's. Those are repetitive, and then we can actually cancel these two out as well. How we're going to do that? So I'm not going to draw the limit anymore, but remember it's still there because it's definitely part of the problem. So we can do 2n plus 2 times 2. Alright, that's not a 2, sorry. 2n plus 1 times 2n factorial, right? This is the expansion of the factorials, and now these two get cancelled. Okay, so what we're literally left with, draw on the right side here, we have n approaching infinity of x squared over 2n plus 2 and 2n plus 1. That's what we're left with, right? And we can remember we want to find the convergence, so we set it less than 1. But if you take a look at the denominator here, we will have to multiply this with the 1, but since we are applying infinity to it, these two values will turn into infinity. So what that really means is since these two are infinity, the value x would naturally be from negative infinity to infinity, right? You can technically do it this way by adding a negative 1, just multiplying it out, but that's just repetitive steps, so I'm not going to do that here today. Alrighty, So let's check the answer key for number 1, and yep, indeed it does converge for all the values. So let's move on to the next problem. I'm thinking we could do D because these two are honestly really similar. And yeah, let's get ahead and to do ln of 1 plus x over 1 minus x. I think that one will be very interesting. Okay, so let's first find the summation for this as well, like usual. And I think the series was 2x. Oh shoot, hold on, let me delete this. This was bad. Yeah, 2x minus 2 over 3 x cubed plus 2 over 5 x power 5th, okay, and so on and so forth. So now we can use this and we can clearly see a pattern here in the numerator, right? We have a 2 all the way through, and we also have a x that increases by a power of 2 every time. And it's very interesting to notice here that we still have x in the first term. That means we're going to have a plus 1 in the summation. And here in the denominator we just have I think this is a 2n plus 1. This ensures that we still have a 1 down here because it's still technically 2x divided by 1 because the 1 doesn't do anything, right? And then we can have the n to make up for the 3 and the 5. So yeah, let's write the summation. N equals to 0, infinity over 2 times, what is this, x, 2n plus 1, and then denominator we can just have 2n plus 1, and there we go, we got our summation. Alright, cool. So now we can move on to the radial test. So limit n approaches infinity. Once again, we do the top term, we do n plus 1 divided by the normal summation formula itself. So we do 2 times x, 2n plus 1 divided by 2n plus 1 and plus 1. And here we write the same thing as the summation formula, so we just do this and we're good. Okay, so we can definitely simplify this. I'm not gonna write the limit again because that's annoying. And we can just I think this simplifies to 2 times x, 2n times x cubed, I think, and then can bring this up here, so 2n plus 1, no factorials or anything, just like that. Denominator we're gonna have, oh shoot, sorry, I forgot the 1 there. We have the 2n, I think this is a plus 3, multiplied by all this good stuff down here, so 2x, 2n plus 1. And now we can do some canceling out, so these two canceled out. This actually cancels out the 1 here, so we're left with let me actually write the limit this time, hold on. Yeah, limit, so just ignore this stuff, limit of n approaching infinity, and we can do x second, I think, yeah, x second over 2n plus 1, that's not a 1, then 2n plus 3, actually that's the only thing left in the denominator. Yeah, and then we can set this all equals, less than 1, and now we can find the values by multiplying these two over to the right side, right? So let's quickly do that. Well, I think we'll get, let's write the left side here, x squared less than limit of n to infinity, and I think the fraction was, so this should go on top, so n 2n plus 3, I believe, and 2n plus 1 in the denominator. And now if you do this, it will give you infinity over infinity, which is indeterminate, so we can't do that. So we can do a sneaky trick where we go like 1 over n divided by 1 over n, and we multiply these with these two values, right? So what this will give us will be x squared less than limit. Sorry, writing on this is not the easiest. Okay, infinity, perfect, and we should be getting 2 plus 3 over n and 2 plus 1 over n, right? Because any integer over infinity is just gonna be 0, so we don't care. So these two will be cancelled out by the limits, so we're left with x squared less than, I think these two will become 1, so it's just x less than 1, right? And then we can put the absolute value because this is plus or minus. And yeah, I think that's gonna be, let's see the answer key for this. And it looks like we're correct. Absolute value of x less than 1. Good job. Okay, let's see what else we got here in the textbook. Binomial theorem. Oh, this one's actually a pretty interesting one. Okay, well, let's try to do this. So what do we have? 1 plus x power p, and we show the Maclaurin series for it. Okay, cool. 1 plus x to the power of p. Alright, is that the question? Yes, that is the question. Right, okay, so I think like, is this, let me see the formula book. I'm not sure if this is on the formula booklet or not, but there is this formula you can use to write the summation. It's pretty helpful. I think it's k equals to 0. I think that's the one they used. Yeah, k equals 0. Then we go to infinity, and then we can do n choose are here, but instead of n we write p because that's the exponent here, and we write k in the bottom. And we can do a is the first value, so in this case will be 1. I think it was np minus k, yeah, but in this case doesn't matter, it's 1. But this should be the formula for that. So yeah, let's plug this in to find the summation for this. So k equals to 0 to infinity, and this is the n choose r, so we can skip that for now. We can do it a bit later. Okay, and this we can plug in as 1 p minus k, so in this case doesn't really matter, and the b should be x, sorry, that's a terrible x power k, and this will stay. Okay, so now let's focus on the n choose r part. So in the formula booklet it says n choose r equals to n factorial over r factorial. I think it's n minus r factorial, something like that. And we can simplify this by plugging in the p and the k. So the p will go for the n place and the k will go for the r place. But the key thing about this is we have to plug it in strategically. So what that looks like is equals to p factorial, I think this is k factorial over p minus k. Okay, so yeah, this is the strategy we're going to use because we know p, like a number, right? So p minus 1, that we can expand that until we get to p minus k, so that we can cancel these two out to simplify this. So what that would look like in practice is p minus 1 all the way to, this is the second to last term until p minus k. So this will be p minus k plus 1, right? The one before, and then we have obviously p minus k factorial itself. And by expanding it this way, we can cancel out the p minus k factorial from the n choose r equation. So now we should be left with k equals to 0 factorial. And we can write this whole thing here. P minus 1 dot 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 p minus k plus 1, and since that's the second last term, that's all we're going to write here. We'll write k factorial times x power k, and that should be the show that question completed. Yep, I think we got it. Okay, do you agree with the previously stated binomial theorem? Yes, it does seem correct because we use the formulas. And let's see part B, why the series only guaranteed for x absolute value x less than 1. Okay, let's take a look. I think we can do the radial test for this possibly. Yeah, let's try the radial test for this. So let's clear the canvas. How will this work? So limit, I think, will be k to infinity, and the first term should be, because it only affects k, right? So we have the top p minus 1 all the way to p minus k plus 1, right? But since this is the whole thing will be minus, this will cancel out the plus 1 later, so this will actually just become p minus k itself, and then here in the denominator we will have the k plus 1 factorial, right? That's just normal, and then we have the xk plus 1 here, can't forget that. In the denominator we have the regular the same summation formula. Can't really talk right now. And then we do dot dot dot. We can do p minus k for this one. P plus minus k plus 1. I'm so sorry guys, my brain is like kind of cooked right now. And then we do that and x power k. Alright, so now we have the limit set up. We can simplify this once again to p. So you see these and this will cancel out, but I think the only term that will remain should be this. No, it's this one. This is plus 1, yeah, so this one will be the only one that remains, and the other one will be gone. Yeah, okay, so p, let's just simplify this further. So equals to, so we have the k factorial on top. Now we have the p minus k on top. Is there anything else on top? I don't think so. I don't think there's anything else on top. This cancels out with this. And k, yeah, the k remains the same, and this becomes the denominator. Okay, so k plus 1, and we can expand this to k factorial, so these two cancel out. So now we're really left with just a few terms. Limit k approaching infinity of p minus k over k plus 1. Now, of course we can't forget these, but since this one is just x over k divided by x over k, we can just write x here. And now we can set this all less than 1, and then we can just do what we did last time, where we multiply everything to the right, because we have x here, so it will be x less than, I think the limit flips, so let me erase this. Actually, this is a bad place to put it. So limit k approaching infinity of k plus 1 over p minus k, and yeah, we want this to become we don't want this to be infinity over infinity, so we can do the same trick we did last time by doing 1 over k and 1 over k. So this will be x less than, I think this will be 1 over 1 if we apply the limit, because this will be 1, and p over k, that will be 0, but minus k over k, yeah, it will be 1. And then since it's absolute value, that doesn't matter. So yeah, we will have once again absolute value x less than 1. And the thing is, like, we know there's a negative here, right? But since it's absolute value, this really won't matter that much. Alrighty, let's see if we got the right answers this time. And let's see, yeah, converges for less than 1. Okay, cool, nicely done. Yeah, let me figure out which problems we want to do next. Alright, we're gonna actually skip number 3 here and jump straight to number 4. So we're gonna be proving that the Maclaurin series for this polynomial is this, to show that question. So why don't we get started here? Alright, let's get started here with this one. I think it was 1 over, what was it? 1 minus 2x. So we can rewrite this as 1 minus 2x power negative 1, right? But that's very, that's easier to read for me personally, but it's up to you how you write it. And I feel like we can use derivatives to do this. That might actually be easier because this is a chain rule. So we have negative, sorry, not negative 1. Let me delete this, hold on. Just 1 minus 2x, negative 2, and of course we got to chain rule the negative 2 out. And we should be getting all this negatives, so these two negatives canceled out. So we should be getting 2 for the first term. And let's do double prime. So negative 2, 1 minus 2x, negative 3, and this one should once again be negative 2, so these two cancel again. This will give us 4, and f triple prime of x would give us, so we have 2, so we have 2 here, and then we have 4 here, so 4 times, oh shoot, it's supposed to be 8, hold on. Yeah, because there's another, so this is already 2, and we have another 2 coming in, so this is actually 3 2's. Oh, other one is just a 2, normal 2, it's not a negative 2, so this one will be 8 actually, so that means we'll have a 8 times negative 3, should be negative, and then 1 minus 2x, negative 4 here, and then we have a second negative 2, so this will also be positive, and we have 6 times 8, that's 48. So yeah, that's all I'm gonna go to because I'm lazy, I don't want to do more terms. And 1 minus, so this will be 0, right, for the 0 term, so I think this will just give us 1. So yeah, we have 1 plus 2x, this should just be equals to 1 factorial, and then we have 8x squared over 2 factorial, and we have 48x, I think this is cubed over 3 factorial, right? And I think that should be the answer here. Yeah, they just have it simplified. We can simplify this as well. 1 plus 2x plus 4x, and this should be plus 8x, if I'm not mistaken. Yeah, 8x cubed, and that should be correct. Yes. And then of course this goes to 2n over x power of n, because we can see the pattern here, this increases exponentially with 2 to the power of n, right? Yeah, so let's take a little water break, and we can do this table here. This pretty much just plugs in the value of n. So the n here actually represents like the summation or the like sum of the terms. So let's say n equals to 1, that will be adding these two terms together, and this obviously it says x equal to 1, so you'll plug that for the x, so this will be, for n equals 1 will be 2, n equals 2 will be 7, and so on and so forth, right? So I'm not going to do that table here because that will take a while, so we're going to jump straight into the conversions part. And yeah, well, like I said, for conversions you will need the summation, but luckily they have already given us the summation. Sorry, not k, this one they use n, I think. So let's just use n equals to 0, infinity. Oh my gosh, what is that infinity I'm writing? So infinity here, and we can do 2n x n, right? And then it says, do you think the values converge when x equals to 1? For this one, you don't even actually need the radial test, because you can just tell that the common ratio r is greater than, absolute value r is greater than 1, because it's 2, right? So no, this one will not converge. You can also do the radial test on your own, but you can just tell it by the common ratio because it's a geometric series, right? So yeah, that's a very easy way to tell. So no. And then let's try this one. So 0.1, that will be the value you plug in for x. And let's try to make a summation for this so we don't have to actually do the table itself. So let's do n equals to 0, infinity. So when we plug in n 0.1, right, it will be the same series as this, but we'll actually plug in the values. So I think this will be just, let's see. Yeah, it's 1 plus, hold on, let me think about this. I haven't done this in a hot while. Okay, so 1 over 5 yeah, let's write in decimals. So 1 over 5, so 0.2, and the next one should be 0.4. Yeah, so on and so forth. So it decreases by, wow, it's actually decreases by a lot. I think it's 0.2n, if I'm correct. It's 0.2 times 0.2, yeah, because 0.04 is 1/25. Okay, so yeah, it's 1/5 to the power of n. Let me double check here on my calculator. Oh my gosh, I forgot how to use my calculator. Okay, yeah, this is right. It's 0.2 power of n, and once again, by the geometric series, right, we know that this r, absolute value r is less than 1, so yes, this will converge, right? Converge. And now we know that this will converge. I think we can actually find the win. Yeah, let's try to find the win. Okay, so let's clear this because I used way too much space. So we know 0.2n, and we can take the radial test for this. So limit of n approaching infinity divided by 0.2n plus 1 and 0.2n. Okay, this is, I think we're all familiar with this at this point if you've been watching the video. And yeah, let's see this part. We can just, yeah, I think we can just do 0.2n and 0.2. These two will cancel out with 0.2n here. So the limit doesn't really matter, and we have 0.2 is less than 1. Let's see what the answer key said for this. I'm actually quite interested. This part. 4. Okay, it just said that it will converge, which it will, right? Which it will. Right. Which values of x do you think the corner series converges? What does it actually do? Okay, because I think we need the actual x for it to solve this. Alright, my bad. We can't actually just take this. That is definitely my fault there. So let's take the, oh my goodness. Okay, we can just like not ignore that as well. So summation n to 0 to infinity. I think we can take the original. So what was that? 2n. Is that the one they're asking for? Yeah, that should be the original. 2n x n. So let's do the radial test for this. So 2n plus 1 times xn plus 1 divided by, oh shoot, limit. I keep forgetting this. Hope I don't forget this on the test. Actually, no, this stuff will not be on the test. So this was just purely for fun. 2n xn. So yeah, if you're worried about this stuff on the test, I don't think Miss Cruz will put on the test because this is like not really, you know, the stuff. I mean, they might put this on the IB test, but good chance they won't, which is good. This stuff is pretty difficult. And yeah, we can just cancel out the n's here, but we will still be left with a 2 times x, and then we can do a limit of n here less than 1. And since the 2 will take the limit with it, this will actually be x less than 1 over 2. But the limit, I'm saying like the n to infinity of 2 doesn't really do anything, right? Since there's no n's left. So we can just cancel it out, and then we can divide 2 to this side. Sorry if I made that very unclear. And yeah, this should be the final answer for this. Yeah, okay, cool. We got it. Good job. Alright, well, I'm probably gonna stop the video here, guys. I think the textbook Ryan sent on Discord, this should be on page 661, and the answer key will be on 1499 and 1498. So if you want to check these out, these are some pretty interesting problems, but these will not be on the test, so you do not need to know these in your heart. But yeah, they're pretty cool, so check them out. And that's all I got. Tony out. Bye bye.